In this video, I want to discuss the idea of Monte Carlo simulations and step through question 1 of assignment RA0. Now, I am not going to solve the question for you, but I'm going to give you enough intuition that I think you could solve it if you reasonably follow its lecture notes as well as the videos that I provided earlier. So, let's begin by defining Monte Carlo simulations. I'll put SIMS for simulations. So a Monte Carlo simulation, I'll write the definition here first, and then we can discuss it. It's a statistical method by which we estimate the result of some difficult to calculate or model process through the use of repeated random sampling. And that's essentially the idea here. We're going to do a lot of repeated random sampling and leverage the laws of probability to estimate the value of something that we really don't have an equation for or a nice way to represent. And a good example to introduce this sort of idea is this question we have on the board, where we're asked to estimate the volume of an ellipsoid, which is a 3D shape. And the reason I say this is a good example to begin with is an ellipsoid has a known volume formula for it. And so what we can do is once we've created our Monte Carlo, we can actually check our work using the known formula. So here's the question. He wants us to provide a function to estimate the volume of the ellipsoid that takes the form of 1 equals ax squared plus by squared plus cz squared. I'm going to rewrite this a little bit. So I'm going to do this. Ax squared plus by squared plus cz squared equals 1. That's the exact same equation. I've just rewritten the lowercase letters as uppercase just to make it more distinct. Each of these letters, A, B, and C, are called coefficients. And what that means is that they're essentially just numbers that we put in there. So for example, we could say 4x squared plus 3y squared plus 7z squared equals 1. And that's a valid equation for an ellipsoid with A set to 4, B set to 3, and C set to 7. The values x, y, and z that we see in this equation, they define the actual shape of the ellipsoid. They define something called the semi-axis lengths of the ellipsoid. Basically, what that means is how far does it stretch along the x, how far does it stretch along the y, and how far does it stretch along the z from some center starting point. That's essentially what these values represent. And so what's the approach that we're going to use here? We're given some hints here. We're told first to generate 3 random discrete values from 1 to 9. So when he says discrete, what he means is whole numbers. And the way that we can generate whole numbers is the sample function. Remember that if I do this, sample, and then I have, let's say, a vector. Let's say I have the vector C1, 2, 3, 4, 5, 6, 7, 8, 9 for 1 to 9. Then I can do this. I can do sample, and let's say this is called vec, and I've used the assignment operator here. I could do sample, pass in what I want to sample, and then the number of values I want to sample. So in this case, I want to sample from here, and I want to sample 1 value. And that's going to spit out one value from 1 to 9. So it might spit out 7 one time, or 5 another time, or 2 one time, or 8 another time, and so on. And you would do this for A and B and C to get 3 random values that we'll use as coefficients here and here and here. That's the first part of the equation, the first part of the question. The next part is he wants us to use another built-in function called RUNIF. That stands for R uniform, and that is a distribution function. So R uniform is a distribution function that will, by default, give us values from the uniform distribution, and that distribution has values that go between 0 and 1. But they are decimal numbers. So you might get something like 0.06157893, blah, 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 and so on. But the values are between 0 and 1, and so we can just use R uniform by default. In order to use R uniform by default, all we do is just specify how many values we want to get out of it. And this is where the Monte Carlo step comes into play. So in this case, we are randomly sampling from a probability distribution some number of values that fall in a range that we're after. And this is what we control to determine how many samples we get. So this could be a number like 100, or it could be 1,000, or it could be 1 million, or it could be much bigger, like 1 trillion or 10 trillion. Of course, as you make this bigger, it's going to take more and more time for R to pull values, but you'll get much more accurate values, or much more values to work with. And the idea here is that we want to pull as much values as we can because that gives us more to work with. But the question maybe on your mind is, okay, why are we doing this? What's the point? Why are we using this R uniform thing? Well, let me draw a very quick diagram here. This is going to look pretty bad, but just bear with me here. So I'm going to try to draw a 3-dimensional axis. So in a 3D space, let's say we got, that's one axis, that's another one, and that's another one. And, you know, it doesn't really matter what we call it, but let's say that's X, that's Y, and that's Z. And you can imagine, though, that the way I've drawn it here, this would continue into the negatives, this would continue, this is in the negative, so it would continue out here, and X would continue out to here. And the ellipsoid, we could say, would have maybe a shape like this. Let's say something like that. Some kind of weird shape like that. It's defined in 3D. It's defined across all 3 of these axes. But what I can do is, well, I could say, okay, we're getting values between 0 and 1. So if we look, this point right here, this is the origin. It's the point with coordinates 0, 0, 0 for all 3 axes. And so then what we could say is, we could say for a point, let's say this is 1, this is 1, and over here, let's say this is 1 as well. We can define a box that covers this corner, a 3D box, a cube that covers this corner of the ellipse, of the ellipsoid. And that cube will cover that corner of the ellipsoid. And that cube, we know the volume of a cube is given as the depth of a cube times its length times its width. And all of these dimensions are 1, as we've established. So that means the volume is 1, whatever units cubed, let's say millimeters cubed. So that would be the volume of this thing that has side lengths of 1 in every direction. And this would cover one section of the ellipse. So it would cover one component of it, and there would be 8 other components that are of the same size in the entire total ellipse. Why 8? Where does that come from? Well, let me explain that. We have three axes, right? We have X, Y, and Z. There are two options, if you will, for each axis. They can be positive, they can be negative. And so when I have three things, two possible options for it, there are 8 unique ways I can reorganize them. So there are 8 what we call permutations or orderings that are all possible from these. And you can imagine that if you have some points in one corner, you have symmetric points, equal points in another corner that just have different signs. And there are many of those. And so the idea here, what we're going to do, essentially, if you're a little bit lost, and I know it can be a little bit hard to follow, is we are going to get this area in here. We are looking for this entire area of this cube thing. But of course, that includes more than what we want. That also includes the extra bit of the cube plus the part that we're after, which is this purple area of the ellipse. And so what we're going to do in this case is simply we're going to effectively use from 0 to 1, we're going to be throwing darts into this cube area. And we're going to see how many of those darts fall within the shape that we're after and how many fall outside of it. And the number of darts that we're throwing comes from this function. So what I mean by that is if we say that this is 0 here, and this edge is 1, and this is 0, and this edge is 1, every time you generate a number from random uniform, it's going to fall somewhere in this cube area. It might be the first time, it might be here, right? It might hit this area. But the second time it might hit here, and the third time it might hit here, and the fourth time, and the fifth time, and the sixth time, and so on. And so what we're going to determine is how many of the total number of hits, how many fell in this first corner. That's going to give us an estimate of the volume of that corner. It's going to tell us, okay, we know how many of the total fell in this case, and if you remember from stats that probability when you're dealing with this can be expressed as an area, then we can estimate the area of this corner of the shape by how many points out of the total number of points fired into this corner actually fit into the shape. And once we have that estimate, let's say we call that, I don't know, little v, then all we have to do is multiply it by 8 and we get an estimate of the total volume of the ellipse. And so that's the philosophy we're going to follow for this calculation. That is probably a little bit of a headache to understand, but hopefully if you play it back, it'll make some more sense. But essentially, just to boil it down in the simplest way possible, we are playing a game of darts. If I wanted to simplify it, let's think about a circle. I'm playing a game of darts. I shoot darts all in this section, and then I determine how many are in the part that I'm after versus the number I fired. That tells me what is the approximate volume of that section, and then I multiply by how many sections I have to get the total volume of the shape. That's what we're doing here. That's the entire point. And then that is going to determine your estimate of volume. The actual theoretical volume of an ellipse is given as this. 4/3 times pi times ABC. Now, notice that I did lowercase abc and not uppercase abc, and that's because these are not the same values. These values here are the semi-axes lengths, and they are not equal to ABC. They're not equal to those coefficients. And in fact, we can actually determine from these coefficients what these numbers should be. And the way we do that is this. We say that, okay, let's assume 393 in this case, since it's an example that he gave us. So we have 3x squared plus 9y squared plus 3z squared equals 1. We can rewrite this in a standard form where we get rid of the coefficients essentially, and we write it like this. X squared divided by 3, or sorry, 1 divided by 3, plus y squared divided by 1 divided by 9, plus z squared over 1 divided by 3 is 1. That's the same because if we multiply 3 by 1 over 3, we get x squared. 9 multiplied by 1 over 9, we get y squared. So we haven't changed the expression. So there's nothing wrong with rewriting it in this way. But now that we have it in this standard form, the denominator here is the semi-axis length. We can use it to find the semi-axis length for that particular axis. So this first value would be for the x-axis. This one would be for the y-axis. This one would be for the z-axis. And so, for example, what I mean by that is the semi-axis length for x squared, we would say, is a squared is a third. And so then a, the semi-axis length, must be root 1/3. Similarly, for the second axis, say b squared is 1/9. So then b must be the square root of 1 over 9. These are the values that you would plug into this formula to calculate the volume of the ellipse based on your ABCs, which you can obtain from this equation. And that's what you compare to your estimate to see how close you are. Now I'm going to pause and talk very briefly about how to use the cat function. And actually, I just realized I didn't really talk about how to use function notation in any of the videos I made previously. So I'll leave this here. It doesn't bother too much. So when I want to use a function in R, when I want to create my own function rather than using a built-in one, I have to use the keyword function. Pretty easy. And so let's if I wanted to make a function for this one, briefly, just the shell of it, I could say something like q1 underscore fqn equals function, and then I open up some round brackets, and this is where I could put any arguments I want, and then I put a squiggly brace, and I put in all the code I want to go inside my function. And this code will be repeated every time I run my function, and I can have the option of putting in some argument here, depending on how I set up my function. Let me briefly pause, and I'll continue shortly. And actually, I just realized something. I did a bad practice myself. That's wrong. You don't use equals. You can. You shouldn't, though. You should use the assignment operator, because this is just an object. So we're binding, remember, we're binding a name to a value, in this case a function. So we use the assignment operator. We could use equals, but we really shouldn't. It's bad practice, and my apologies for using it and creating any sort of confusion. But in here we would do something, and then if we wanted to use the function, we would just do this, q1 underscore fqn, the name of the function, and then open up some brackets, put in some input if we specified it, and then it'll run and it'll give us some input or output if we've told the function to do that. It really depends on how you write the function, but that's how you would do it. The other thing that I want to talk about is we can use briefly, I'll mention, is you can use scientific notation to represent big numbers. So to use scientific notation, we can use the symbol capital E. Remember, that's short for times 10. So as an example, 1e4, that's the same thing as 1 times 10 to the power of 4. And 1 times 10 to the power of 4, again, remember, we can just move the decimal to the right 4 times. So 1, 2, 3, 4 to get 10,000, right? And so that's a nice convenient way. Instead of writing 10,000, you can just write 1e to the 4. Or for bigger numbers, you just 1e to the 5, 1e6, 1e7. So just something to keep in mind. And the last thing I'll mention, the last hint for this question, is the cat function that he's specified here. So you see an example but I just want to clarify what's happening here. So when we use the cat, the combining function for printing out text, it's a nice way of printing out text where we can combine variables and text to get a nice little output. So what's going to happen here, if you look at this line, is whenever you see something in quotes, that's something that'll come out directly in the input. But then we have a comma and then another value a. So when we put this in cat, we're going to see this thing that we put as input. Then we're going to see this value pulled into it. And then if you have a comma and some more text, that will show up. So let me open up just the R GUI to show you. And I'll use the keyboard shortcut Control L to make it smaller. So let's look at this. Let's say add A is 9. I'm sorry, A is 3, B is 9, and C is 3. So A, B, C. Then I can do this. Cat, my values were A, and also B, and finally C. And then now we're going to add this \n. \n means the output should go to the next line, meaning that it'll add essentially like a space between lines. And that becomes important if you're running this over and over again. And have a look at this. It'll say the text my values were. Then with a comma, it'll fill in this value, which we know is 3, and it'll just put it in the text. Then it'll continue after the next comma with some more text. Then when we hit the second comma, it'll substitute the value B, which is 9, and print it here. And similarly for C, and we get this nice little output. And that's exactly what he's expecting for this question. And what he's going to look for is to tell him what values you generated, the volume that you estimated, and then actually what is the volume that you calculated from the equation I mentioned earlier. And so that is the help for question 1. I hope you found it useful.